Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing sediment output options. So where you can find the sediment output options are going to be in the Run menu, Quasi-Unsteady Analysis for Sediment, and then in this Options dropdown, the second value or option here is Sediment Output Options. So go ahead and select that. This dialog box is going to be the focus of this video lesson. If you're interested in following along online in the user's manual, I'm going to leave a link to this page here in the description of the video. This is the HEC RAS 1D sediment transport, and then here are the topics we're going to be discussing. All right, starting with output level. So that would be the first drop down in this dialog box, and boom, here it is. Output level. Okay, so the options for output level are 1 through 6, and there's also this only customized at the bottom. I'll talk about that later. But 1 represents the least amount of output, and then 6 represents the most amount of output. The user manual mentions that output 4 is the default, but there's also 1, 2, 3, 5, and 6 to select. What that means is output 1, for instance, let's just check out what the user's manual has to say. Here it is, output level. And then if we scroll down to level 1, it actually tells us exactly which variables related to sediment that are written out in the output file. So we have invert elevation, invert change, water surface elevation, and then the mass or volume bed change cumulative. If you see this CUM, that represents cumulative, meaning the value is summed up over all the time steps starting at the beginning of the simulation. And we have the option for it to either be mass or volume. That's kind of a common theme amongst some of these variables. So we'll touch on that in just a little bit later. All right, so that is level 1, not a lot of data. And then level 2, it adds more data. So what it does is it says level 2 includes all the variables from level 1. And then level 2 also includes hydraulic parameters and so on and so forth, such as the flow rate, the average velocity, the shear stress, and what else do we have in level 2? Okay, so I guess that's it, at least according to the user's manual. Level 3 includes everything from level 2 and so on, and then it keeps going. Level 4 is the first level where the sediment data is subdivided into the 20 different grain size classes. At least I read that somewhere. So for levels 1 through 3, all you're getting is the total mass or total volume of all the sediment, but it's not broken down into the specific grain size classes, and that information could be very important and wanted. So that begins at level 4, and of course is also true for levels 5 and 6. But the user's manual mentions that this can really increase the amount of size for the output file because you have different cross-section data, different cross-section points, different sediment data, times the at most 20 different grain size classes and so on for all these different variables. It can really add up and quick. So 1 through 6 is what we have here. Say, for instance, there's a particular variable that isn't included in these variables here for lists 1 through 6. You can just select output level 1 and then come over here to this button, select customize variable. This is going to open up a dialog box that allows you to select a custom variable here that wasn't even included in that level 1 through 6. So for instance, I come down here to D50 cover that includes that variable. I can just click D90 cover and then the arrow over. That also adds it to the list as a manually entered variable to add. So I can click OK. And now I see those two variables showing up over here in this list box. I can clear them out as well just by clicking clear. Or if I want to add them back in, I'll just add them back in right here and then click OK. And if, for instance, these are the only variables that I want, I don't care about the default variables that come with a specific output level, not a problem. I just come down here and click only customize variables, and hence these are only the variables that will be written to the HDF5 file or any of the other output type of files that are selected. Okay, we'll talk about that a little bit later. And before we leave this drop down, I do want to point out that there are a lot of variables to select from. This is actually a drop down here. So there's probably over 100 variables, and they're sort of grouped up too. Like at the beginning, we had common 1D results, 1D hydraulics, 1D cumulative control volume, and so on. So lots of different options to select from. Okay, I'm going to go ahead and clear those variables and then just set this back to level 1. The next drop down here is mass or volume. So you need to select either mass or volume. And what this is going to do is it's going to return the selected results from your output level or your manually selected variables for mass or volume, but not both. Now, some variables don't take into account mass or volume, such as shear stress or flow rate, but a lot of the sediment properties do rely on either mass or volume. I believe volume is the default. The mass is just the volume times the unit weight, and then the volume is just the mass divided by the unit weight. So you can go ahead and make that conversion. And that unit weight, of course, is dependent on the grain size class itself. However, it's defined in the gradation. If you want both mass and volume, you can select one from the dropdown, like volume, and then over here in the custom variables, go ahead and select whichever mass related variables you want to include. Okay, the next dropdown here is output increment. Now that means the increment that the output is written to the output file. So it could be once for every computation increment, flow duration, hours, or days. So hours or days are like fixed time durations. We all know what that is. The computation increment and flow duration, this has to do with the flow data, the flow file that's defined in the boundary conditions. So if we go up to edit and then quasi unsteady flow sediment, click on our flow series data. Now what in this table, we have the different flow rates, and then we have the flow duration and the computation increment. Now the computation increment has a ceiling or a maximum, which is the flow duration. So the computation increment is never going to be larger than the flow duration. For instance, I could go ahead and make this zero point 0.1 or zero point 0.2, probably some sort of number that divides evenly. Right, so right now I'm just using 1 hour and zero point 0.1 hours for flow duration and computation increment. Let's go ahead and say the flow duration is 4 hours and the computation increment is 0.5 hours, just for this first time period. Okay, so I'm just going to click OK. So that means if I'm over here and I set the output increment to the computation increment, that means every what I say, zero point 0.5 hours, every 30 minutes, with a new set of variables would be written to the output file. If I set flow duration, then it would be 4 hours because it's 4 hours, at least for that first time interval. After that, it was back down to 1 hour. There's pros and cons between whatever you select for this output increment. So for instance, if you select computation increment or flow duration, these results focus on high flows and changes in the sediment data. So you're going to get all the action. You're going to see what happens and when. Because the computation increment is usually much smaller during higher flows, and the flow duration increment is usually smaller when it comes to changing flows. But if you select hours or days, you could very easily miss some of the interesting sediment activity in the simulation if it all takes place within the same hour or within the same day. However, if you do select hours or days, this is a constant time period for the entire simulation. And the advantage to that is that if you play back the results in an animation, it will look normal. It won't look distorted by different profiles or different time steps within the playback animation being different durations. So there's different ways to think about it and different ways to set your output increment, depending on what's more important to you. All right, the next field down here is primary output interval for the multiple of output increment. So right now it's set to 1, that's the default, and that basically means if it's set to days, that means it outputs once a day. If it's set to hours, it output once an hour. If I want it to be output once every 3 hours, I would set this to hours. I would set this value to 3 hours. So the output increment we select here sort of works in tandem with this primary output interval. This could get a little bit fancy if, for instance, we set it to computation increment. That means the output would be written every 3 computation increments, or every 5 computation increments, or every 1 computation increment. And then same is true with the flow duration. It could be every flow duration, every 3 flow durations, every 12 flow durations. That's how that works. Further down, there's a checkbox here for cross-section bed change output. This is a optional feature because it's a checkbox, and by default, it is unchecked. This is a very computationally expensive routine for HEC RAS to run. It's turned off by default because it's a very memory intensive process. Each cross section data point on all cross sections are saved. And because it's very computationally intensive, if you are using it, you check this on. By default, it's off. And then you can specify the number of increments between cross section outputs. So for instance, if this was hours and we wanted it not every hour, but maybe every 3 hours, that's how we would set that. If we put a 10 here, this would write cross-section data for every 10 profiles or every 10 output increments. If none of this data was set here, by default, HEC RAS reports variable values after every 10th computational increment and at the end of every flow duration. So that's referring to these two values here. Below that, we have a box for our Sediment hot start options. Yes, Sediment has hot start as well. If we wanted to initialize our data from a simulation using a hot start file, we'd go ahead and check this checkbox. Then we'd have to specify what data we're actually reading in from that file. And our options are gradation and bed elevation, gradation only, or bed elevation only. So go ahead and make that selection. After that, we need to navigate to the file that was written that has that data. So we click Browse, we navigate to the HDF file. It's going to be the HDF file that is associated with the plan. So it's going to be the project name dot key number dot HDF. That's where that data will be saved. And then after that, we need to specify the hot start date and time. So I typed in the first hour of August 1st, 1975. HEC RAS will initialize the model with the closest output profile from the selected HDF file right here, using the closest hot start date and time it can find from that file. And what it's going to initialize is the gradation and the bed elevation, because that's what I told it to initialize. There are a few points I need to make about this hot start. The user manual mentions that the output file used, that HDF file, must use an output level 6, which is like full details. And also, when creating that output file, it needs to use volume, which I already have selected here. Also, the new model that is reading in the hot start data must have the same cross sections as the output file. And the third and final comment is that the gradation hot starts require the same bed mixing algorithm to be used. So bed mixing algorithm refers to the sediment data, and then sorting method right here. The options here are Thomas, active, and Copeland. For your simulation, if it's using the active sorting method, for instance, it cannot use a hot start from Copeland or Thomas, and vice versa. It has to be using the same sorting method or mixing algorithm, it's called. Okay, so this is in the sediment data. That's where I opened up this dialog box. That's in edit sediment data. That's how you get there. Okay, we're back to the sediment output options dialog box. A few more things here at the end is these are checkboxes to write the output variables to specific output file destinations. Now, by default, recent versions of HEC RAS, presumably my version 6.6 here, automatically writes output files to that .hdf file, HDF5 file, excuse me, and those are read in by the sediment plotter. In a later lesson, we'll run the simulation and look at results and see how that works. But right now, we're just talking about how to write those files. It's automatic. And then these checkboxes are, I think by default, the first one is checked on. This is how to write classic output to the .o file. The second one would be to write legacy binary output. And then the third one is to write data to a DSS output file. If you do go with this DSS output file, you need to select which data, like all or concentration, flux, cumulative flux, and so on. And you also have the option to specify a river station. So what you do is just go ahead and click on this radio button, specify the river, and then the reach, and then let's add 300 and click OK. And then I'm guessing that added in. Okay, yeah, so I just kind of have to scroll down here. 300 is now in the mix. So when I click OK and then compute, that data will be written. Here is the directory on my computer, on my local machine, that has the project files. And right here is that DSS file. It's the name of the project, .p01.sed.dss. And then the .hdf file is right here. That's project1.p01.hdf. So it's plan1.hdf. And then further up here is the output file. So I ran this off camera, and then these output files ran lesson 56.001. That's more for the static hydraulic data, which you can view things like cross-section and profile data for. Okay, well, that's it for this lesson. What we talked about was using the different sediment output options when running a quasi-unsteady simulation in HEC RAS.